Deep within the heart of our sun, a violent celestial furnace burns with unimaginable intensity, fusing hydrogen into helium. But there is a byproduct of this fusion that defies all conventional logic: the neutrino. These subatomic particles are produced by the trillions every single second, yet they remain almost entirely undetected by human instruments. They are the ghosts of the particle physics world, carrying secrets from the core of stars across the vast, freezing emptiness of space. To understand why neutrinos are so revolutionary, we must first accept that the world is not solid. Every second, roughly 100 trillion neutrinos are streaming through your thumb, passing through your skin, your bones, and the entire diameter of the Earth as if it weren't there at all. Unlike protons or electrons, neutrinos possess almost no mass and carry no electric charge. Because they don't interact with electromagnetic forces, they are effectively invisible to the matter that composes our physical world. The mystery of the neutrino deepened when physicists realized these particles possess a strange trait known as oscillation. For decades, the standard model of physics insisted that neutrinos were massless, but the phenomenon of flavor shifting, where a neutrino changes from an electron type to a muon or tau type mid-flight, proves they must have mass. This discovery shattered our existing theories and forced scientists to accept that our current rulebook for the universe is incomplete and fundamentally flawed. Detecting these ghostly entities requires extreme engineering. Because they ignore solid matter, we cannot use standard silicon sensors. Instead, scientists have built massive observatories buried miles beneath the Earth's surface or deep within Antarctic ice, such as the IceCube Neutrino Observatory. By filling enormous volumes with ultra-pure water or ice and surrounding them with thousands of light-sensitive detectors, we wait for the rare, once-in-a-blue-moon collision between a neutrino and an atom. When a neutrino finally hits an atomic nucleus, it produces a tiny, fleeting flash of blue light known as Cherenkov radiation. This faint glow is the smoking gun that tells us a particle has arrived from deep space. These flashes are not just data points, they are cosmic coordinates. By tracing the direction of the light, astronomers have begun to build a neutrino map of the universe, allowing us to see through galactic dust and gas that normally hides the most violent events in the cosmos. Beyond simply studying the sun, neutrinos are now acting as a new type of telescope. We have captured neutrinos originating from blazars, supermassive black holes at the centers of distant galaxies firing jets of radiation at near the speed of light. Because neutrinos aren't deflected by magnetic fields like charged particles, they travel in perfectly straight lines, pointing back to their exact origin point in the universe, effectively opening a new era of multi-messenger astronomy. Perhaps the most tantalizing theory involves the right-handed neutrino. Standard neutrinos always spin in one direction, but if their counterparts exist, they could be the elusive dark matter that makes up the majority of the universe's mass. If we can prove the existence of sterile, heavy neutrinos, we might finally explain why the universe contains more matter than antimatter, solving the biggest imbalance in the history of the Big Bang. As we refine our detection methods, we are essentially turning a flashlight on the dark corners of the vacuum. We are moving from a universe of light to a universe of information, where even the smallest, most invisible entities provide the missing pieces of a cosmic puzzle. The neutrino is no longer just a ghost. It is our key to unlocking the physics of the next century, proving that what we cannot see is often far more important than what we can.